Welcome to our second asynchronous session. Today I'm going to talk about topics in Unit 2. Unit 2 covers a variety of topics, but it seems to be all about quadratics. I'm going to focus more specifically on the transformations of quadratic functions. Alright, so let's talk about some examples of parabolas in the real world. We can see that the Golden Gate Bridge forms parabolas, and the trajectory of different flights of balls or any kind of projectile motion, we call it, is an example of a parabola. What I wanted to point out here is this picture of this basketball because it has specifically something to do with one of your project questions in that lesson. Right? It talks about shooting a basketball and solving a quadratic to figure out when the basketball will go into the hoop. Right? And they decide that that hoop height right there in the beginning is, they define that, right, to be the x-axis so that when you're solving for the quadratic equation, you can find that value out. It also asks about what the other solution represents. All right, and as you can see, when you shoot a ball with any kind of arc on it, all right, the ball is at the height of the hoop 2 different times. Right, because it has to go up first, and it's going to pass the height of the hoop, and then it's going to come back down to be at the height of the hoop again. So I just wanted to point that out. All right, so this is called the vertex form of a quadratic. All right, and the vertex is located, you can see here, at HK. These HK are numbers. They are the point where it is either at its minimum or its maximum of the parabola, the vertex. Let me go back. All right. Okay. All right, so A determines, in this case, if the parabola opens up or down and how wide it is, and we'll talk more about that later. Right, a parent function, right, is the simplest form of a function that still maintains the definition, shape, properties of the family function. So in the case of our quadratic, the quadratic parent function is f of x equals x squared, and there you can see what the graph looks like. Right? All right, so we can take this parent function and transform it to get any other parabola we want. All right. There's 3 types of transformations that we'll be talking about. One is called a translation, and that just means moving it up or down or left and right, but no rotating. We can do what they call a dilation. That's where we do actually change the shape of it, but we stretch it or we squeeze it. We make it wider or thinner, right? But we don't add any curves or anything else to it. And the last thing we can do with a quadratic is reflect it. We can flip it over the x-axis or over the y-axis. So when we do a vertical translation to our parent function, all we do is come out to the end and we add or subtract the number. So if we're adding a number, we can see that it moves that parent function up. If we subtract some number, that moves the parent function down by that number. In your lesson, when you add a number on the outside like that, they call that adding a number outside the argument. All right, and when they're talking about the argument, they're referring to the x terms. Right, so the argument would be anything where the x's are. And if you go outside of that, then we say it's outside the argument. So let's take a look at one of those real quick. Let's talk about then what is the equation of the pink parabola. Here we have our parent function, the blue parabola, at y equals x squared. And we want to write the equation for the pink parabola, which has just been shifted up 2. Right, so to write that equation, we just go to the outside the argument at the end and just put plus 2. If we had a function that was shifted down below this one, we would put minus however many it was shifted below. And the easiest point is just to look at the vertex to decide that. A horizontal translation moves the parent function left or right by whatever number, and this is where it's kind of opposite of what you might think that it is. If you add a number, like if you do x plus 5, that actually will move the parent function to the left, not to the right. Right? It's kind of switched from what you think. X minus some number would move the parent function to the right. Right? Right? And when we replace the x's, notice where these parentheses are is where we would have just had x in the parent function. When we replace that x with something in parentheses, like I've done in this case, we call that adding a number inside the argument. Okay. So let's practice doing that for a second. The blue equation parabola is the parent function y equals x squared. And I've taken that function and I've shifted it to the left 3 times. We can tell because the vertex was at 0, 0, and now the vertex is at -3, 0. So I've shifted it to the left 3. So we would write that equation as parentheses x plus 3 squared. Remember, when we move it to the left, it's a plus. When we move something to the right, like I've done in this case, then we subtract. So what do you think the equation of this parabola is going to be? That's right. You replace the argument with x minus 5. And then subtracting 5 actually performs a shift to the right. So let's go ahead and put that all together with what we've learned about the vertex form. So here's the vertex form. And I told you earlier that the h represents the x value of the vertex, and that the k represents the y value of the vertex. Well, notice that inside the argument where I have the x minus h here, right, if I'm shifting it to the left, then that does a left or right shift, or a horizontal translation. And it's the opposite because we have a minus sign here. That's why minus 5 shifts it to the right, and plus 5 shifts it to the left, because we're subtracting the opposite. So we saw that adding or subtracting a number inside the argument like that performs that kind of shift, and that makes sense, right? Because that's the value of the new vertex. And same thing with the k, right? Adding something to the outside at the end is your vertical translation or shift up and down. So that makes sense that now this form, we can see both here is representing a horizontal shift in this form, and this is representing the vertical shift. We'll talk more about the a term later, but that has to do with, remember, how wide the parabola will be. All right, so let's practice. The blue parabola is a translation of the parent function. All right, so now let's see if we can write that equation in vertex form. So here's the parent function right here at f of x equals x squared. And let's see how we've shifted it. When I'm looking at this picture, I see that I've shifted it down 2 and to the right 3. All right, so I'm going to go ahead and I'm going to start out with my vertex form. All right, and where h and k is, I'm going to replace it with the new vertex. So remember, it's kind of like x goes with x. That's how I know this. H right here is the x coordinate of the vertex. So right there, I should replace it with 3. So right in there, I should replace it with 3, where I see the h. And for the k, I can see that I've shifted it down 2, so that's going to be -2 at the end. All right, so we plug in the 3 for the h and the 2 for the k, and we come up with this equation. The a in this case is 1, because we got from the parent function. So I don't need to include it, right? It's assumed 1 out here. And finally, the equation for this blue function is listed here in vertex form. All right, so your lesson talked a lot about then taking that and talking about mapping statements. So let's talk about mapping statements for translations, just shifting something up or down or left or right. Right, the function that they start with is called the pre-image, and you see them in your lessons denote that as p of x. So that's where you're starting from. And then that I of x function you see over here, that's called the image. So they denote that as I of x. So it's like, hey, we're starting from p of x, the pre-image, and what do we have to do to this function to transform it into the new function I of x? How did we have to, in this case, shift it? So we want to write that mapping statement just telling us how we shifted the original function, the pre-image, p of x, to get it to be to where I of x is. All right, so you might see questions written like this. So given that p of x is equal to x squared plus 3, what is the mapping statement that will produce the image I of x? So how do I get p of x to where I of x is? Well, simply we can see that I'm going to have to take this, here's the vertex, I'm specifically looking at the vertex, and how do I get that vertex to line up and be on top of where this vertex is? Well, I can see that I'd have to go to the right 5 and then down 2. So when I write a mapping statement, that's pretty much all I'm writing. So to get our original function p of x to map to the new function, see that's what that little arrow means. I'm going to map it to. I show what I did to p of x. And remember, a minus 5 does our inside the argument, shifts it to the right. So they're just saying that, hey, we take our original function and we move it to the right 5. That's what indicated by this minus 5. And then down 2 is indicated by the minus 2 on the outside of the argument. Right? So inside with the parentheses, remember, does your left and right shift, and it's opposite of what you think. So minus 5 would shift it to the right. Okay, so that's called a mapping statement. Let's say, though, that I wanted the equation for I of x. Right? Then we could easily go ahead and write that, because we know that I of x is the translation from the mapping statement of what p of x is, except for shifted to the right 5 and down 2. All right, so I'm going to go ahead, and we know that p of x is equal to x squared plus 3. All right, so notice that I take the x minus 5, that's doing my right shift of 5, and I plug it in where I see the x's in p of x. If I had another x term, like if it was x squared plus x minus 3 or something, I would replace every x with parenthesis x minus 5, wherever I saw the x. That's what we call replacing something inside the argument, right? I replace the argument with x minus 5. And we still have a squared up there, right? So here I replaced all that x from here with x minus 5, and I still have the squared. Then I still have plus 3 from the equation, but we also subtracted 2 to go down 2, so I add that at the end. All right, and then finally I can do 3 minus 2 is 1. So if I really want the equation for I of x in vertex form, here it is, the x minus 5 squared plus 1. All right, and we saw just from the vertex form of an equation, you know, that if I were to write the equation of this, notice there's no a value in p of x, so a is 1. I would say that I would write the vertex here where this minus 5 and plus 1 is. So the vertex is at 5. Yeah, there it is, indicated by this minus 5 inside the argument, and y value of 1. All right, so either way. So here's a question that comes right out from one of your checkpoints. In the following graph, p of x, the parabola is opening upward with a vertex at -5, -9, and it is the graph of the quadratic function p of x equals the quantity x plus 5 squared minus 9, and represents the pre-image for a transformation. So they're saying, hey, this is blue one here, this is where we're starting from. What do we have to do to get it to be where the I of x is, right? I'm going to go ahead and tell you that I of x is a parabola opening upward, and it has this vertex at 7, -3. All right, and it is the image, meaning we went from p of x to I of x. Let's go ahead and write the mapping statement for the transformation. All right, just like we were doing before. So remember the mapping, I want to say, what do I have to do to move this function to get it to be that function? In this case, they're giving you the vertexes so that if it was too hard to tell by the graph where these points are, you could look at the points that they gave you and see how they moved it to get from one vertex to the other vertex. So let's take a look. To get from this x-coordinate of the vertex on p of x to this x coordinate for our image I of x, I could count. According to this, the vertex is at -5, right? And I have to go all the way over to +7. All right, so that is a difference of 12. So we shifted this thing to the right 12 units. If you're looking just at the points, you could have said 7 minus a -5 is 12. All right, so we know that when I write our mapping statement, that I'm going to have x minus 12 as the argument. Now I'm going to count how much we go up. Well, to get from this y value of the pre-image to the y value of the image, we see that we have to go up 6. And if you couldn't tell that from the graph by counting, you could again look at the vertex points that they said, and went from the image point, so I'm going to take the image, which is at -3, and subtract the pre-image. So I would say -3 minus a -9. A minus is a plus, so -3 plus 9 is +6. All right, so we went up 6. So let's go ahead now and write the mapping statement. So we're going to say to get to I of x, we just take p of x, and this indicates, remember inside the argument, a shift to the right of 12 and then up 6. So it's really not as bad as it looks. Right? That's how we write a mapping statement. We're just saying what we're doing with the shifting. So to the right 12 and up 6 is how to read that. All right, so now we've talked about translating a function. That means just moving it up and down and left and right. The second type of transformation we're going to talk about is called a dilation. All right, and a dilation is changing the shape. It's of the parabola. It's squeezing it or it's stretching it. All right. So again, here's our parent function x squared. All right. The a value, as I kind of mentioned earlier, that's what controls the width of the parabola. Right? If it opens, and also if it opens up or down. Right? If it's a positive value, it opens up. If it's a negative value, it opens down. All right. It turns out that if you make the a value a large number, larger than 1 absolute value-wise, like 2, 3, 4, 5, or even -2, 3, 4, 5 if the graph was going down, it makes the parabola thinner. It would make it skinnier. If you give me a value that is between 0 and 1, like some fraction, like 1/2 or 1/3 or 0.2, in between 0 and 1, that takes us from the parent function and makes it wider. So for example, here's the equation f of x equals 2x squared. We can see that it's been squeezed, right, toward the y-axis, right? And they call that a vertical shift. And it is thinner. You can see it's a little skinnier. On the other hand, if I went ahead and replaced the a value in the front there with a fraction, like in this case 1/2, you can see how this green graph is wider than our original parent function of x squared. All right, so just like before, when we were doing mapping diagrams with statements with the translations, we can also do it with a dilation. So you might have seen this in your lesson too. A vertical dilation is when you multiply the entire function by some number on the outside of the function, as you can see in this top lesson here, on the outside. Right, a horizontal dilation is when you go inside the argument and you multiply it by some number. Okay, there's a slight difference between the two, and I know it might have been confusing in the lesson about exactly what is the difference between the two. All right, when you do a vertical dilation, right, the y values of each point on the pre-image are going to be multiplied by k. But the x values are going to stay the same. So if the x values are staying the same, you're like stretching the function up and down. Whereas what they would say is you're moving it toward or away the y-axis. Okay? But when you perform a horizontal dilation, that means that you're multiplying k inside the argument by some number, right? K is some number that you're multiplying inside the argument. Then you're performing what they call a horizontal dilation. That means you're moving the graph toward or away the x-axis. All right, and the x values of each point on the pre-image are going to end up being actually divided by whatever that value of k is. However, the y values are going to stay the same. So I know we need some examples to go and demonstrate what that means. Here you can see that I have the parent function x squared as the red parabola. And in this case, I'm going to take it and I'm going to perform our vertical dilation, right, and multiplying it by 2. All right, so we get this new function that I of x, our new image, is equal to 2x squared. Notice that in this case, it's the y values that have changed, but the x values haven't. So in this case, they've taken this graph, and for each x, notice in the original equation, 1, 1 is on the graph. And in our image, 1, 2 is on the graph. So the x coordinate stayed the same, but the y value is what got multiplied by 2. It was 1 before, now it's 2. So another example here is in the original example of the original pre-image x squared, when I put in an x value of 2 and for the x, I get the output of 4, and we can see that on this graph. All right, so on the new graph, on the image, if I plug in a 2 right here for the x, then I squared and multiply it by 2, I get 8. So we can see this value of the y value of 4 has now become an 8, or been multiplied by 2, but we kept the same x value. And you can see that here is demonstrated by what we're doing with these points. See, the y values got multiplied by 2 since we performed this vertical dilation. Let's consider the pre-image. P of x equals the quantity x plus 3 squared minus 5. So there's our equation of a parabola in vertex form. And we know that the vertex, if it asked, was at -3, -5. Remember, that's opposite what you see inside there. So when it said a +3, I knew the vertex actually was at -3. So watch out for that. It's an easy mistake to make when you're first learning this. And we can see that in all the pictures of the graphs, though, that the vertex is in fact at -3, not positive, -3, -5. All right. So in this question, we're asked to, hey, do a little matching. Let's match up graph 1 with either mapping statement A, B, or C. And same thing, which one goes with graph 2? Which one goes with graph 3? Again, this was one of the questions out of the checkpoint that I kind of altered a little bit. So how do we know? How can I look at these pictures and decide which one of these dilations was done? What did they do from the original equation P of x to get to I of x? All right, and one of the ways you're going to be able to tell is by looking at what the new points are on the new graph. That's why we talked about, hey, if we did a vertical translation, remember, it's the y values that changed, but the x's stay the same. All right, and if we did a horizontal translation, the y values stay the same, and it's the x values that change. All right, so that's why they went ahead in each of these cases, and they told you what points were on the pre-image so that you could try to find the corresponding points on the image. So let's take a look at this one. On our original diagram, the vertex here is at -3, 5. And now I can see on this new parabola that the vertex has been shifted up. But look, in this case, the x-coordinate hasn't changed. It's still at -3. All right, it's the y value that's changed. So since I know that it's just the y value that's changed on the vertex, I know that we must have been doing a vertical dilation. And on a vertical dilation, we multiply it something on the outside, right, of the equation. right, on the outside of the argument, not on the inside. So remember, like here's in this example A, when I have 3x inside the parentheses, that's inside the argument. That does our horizontal shift. This one, though, when we have it multiplying on the outside, right, of the argument, that is what's doing our vertical shift. And here's another one that's doing a vertical shift on C. So now I know it's either between B or C that matches up with graph 1. So which one? Well, let's see if we can find out. So they tell me that these points are on a new one, -3, -1. Well, the x is the same, so what do we have to do to this -5? What do we have to multiply it by to get it to be -1? That's the question you should be asking yourself, because we know it's a vertical dilation. Right? Remember, we know that because we can see that the vertex has just been shifted up. So not left or right, but just up. The x-coordinate's the same. And yes, to get the point to be from -5 to -1, we would have had to divide it by 5. And dividing by 5 is the same thing as multiplying by 1/5. So now we know that graph 1 should match up with B, mapping statement B. All right. Now let's take a look at graph 2. So now if I look at graph 2 and I'm looking at the vertexes again, I'm seeing what happened to the vertex. I can see that the vertex from our pre-image just kind of shifted over to the right, but the y value stayed the same. So it's the x value changed, but not the y value. Right? So that indicates that we are doing a horizontal dilation. Horizontal dilation, right? So, and that means we're looking for a number being multiplied inside the argument. Inside the argument. And in our case here, we only have one option that has a value multiplied inside the argument, and that's option A. But let's go ahead and let's examine it a little closer so we can see that how we get from P of x to I of x in that case. All right, so here's our points that are on our original pre-image. All right, now let's take a look at the points that they have on the image. So this first one, -1, -5, we can see that that is the new vertex of our image. So let's see what changed. Well, we see that the y value didn't change at all, because that's what happens when you do a horizontal dilation. But what was done to -3 to get it to be -1? Well, in order for that to have happened, we would have had to divide, right? What do we have to divide -3 by to get it to be -1? Well, the answer is 3, right? -3 divided by 3 gives you -1. And if you had to, that's how you can know that these points, and if you went ahead and compared all the other points, you would see that that's what they did, divided the x coordinate, right, by 3. Again, it's opposite of what you think when you're doing inside the argument. You know, before, like when we're doing a right shift, we subtract, and when we're doing a left shift, we add. When we're doing a horizontal dilation inside that argument again, when it says like when multiplying by 3 is what it does to those points, the x-coordinate points is on the graph is divide them by 3. So by process of elimination, we know that this last one here matches up with graph C. Graph C. Right, we have to multiply all the y-coordinates by 2. And then you can see that's what they did. -3 stayed with -3. -5, though, became -10, so that means we multiplied by 2. And you can see that works with the rest of the points as well. All right, so let's go ahead and convert from standard form to vertex form, or the other way around, rather, from vertex form to get it back to standard form. Because I saw a few questions in your projects that required you to do that, and I'm not sure that the lessons covered it. Luckily, it's not too hard. All right, all we're going to do is we're going to take our vertex form and we're going to basically just simplify it using order of operations. That's really all we're doing. So if I look at this vertex form right here, this equation we have. Order of operations would say, well, we do parentheses. Well, I can't add an x and a 3, so I can't simplify that anymore. All right, then I got to do exponents. Oh, we do have an exponent. We're raising that quantity, x plus 3, to the second power. And as what you got to remember is that x plus 3 squared does not mean x squared plus 3 squared, right? It means the whole quantity is being multiplied by itself. So x plus 3 squared means x plus 3 times x plus 3. Then you got a FOIL, okay? So here I went ahead and expanded the x plus 3 squared into two binomials, so you can see that that's what that means. X plus 3 squared means x plus 3 times x plus 3. Now let's go ahead and FOIL. So remember, we times everything by everything and combine like terms. And when I did that, I got this result, that x squared plus 6x plus 9. All of that is still going to be multiplied by this 2, so that's why I left brackets around it. All right, so now let's go ahead and distribute that 2. All right, so I multiply all those terms inside there by 2. And we end up with 2x squared plus 12x plus 18. And this minus 4 just dropped down. It's still there. It's still on the outside. You know, and finally we have like terms here. 18 minus 4, which is 14. Okay, now we have it in standard form. So it really just as simple as following the order of operations to simplify until you get it into what we call the standard form of a quadratic. All right, so you can go ahead and pause your video and see that if you can write this one in standard form. If I happen to ask you, we know that this parabola does open down because the value of a is negative. All right, so we know that it opens down. Now let's go ahead and state what the standard form is. So here's our standard form, right? ax squared plus bx plus c. I'll give you a moment to copy this down, and hopefully you got that same answer. All right, once again, if you have any other questions on absolutely any topics, it doesn't even have to be in Unit 2. You know, go ahead and we can either arrange a one-on-one session, a Q&A session over Adobe Connect, or go ahead and email me, call me, message me, whatever works best for you.